Hello friend, in this video I will be talking about decision tree, and I will be using Python for the implementation of this particular supervised machine learning algorithm, which is basically used for performing classification type of analysis. So over here, in context to decision tree, what I will be using is I'm going to use the Iris dataset, which is very popular, and I have already downloaded the dataset and I have kept it inside my system. Or if you wish to use the preloaded dataset of Iris present inside the sklearn, that also you can use it. But I downloaded it so that I can demonstrate, I can show you right over here. So this is how the dataset would look like, and there has been basically three type of classes. One is Setosa, Versicolor and Virginica. So this entire data set has been distributed evenly in context to these three classes. Okay, so first what you can see right over here is I'm reading the data from the following path using the panda, and I'm storing it inside a reference called df, so data frame. And then what I'm doing, well, let's do one thing. Let me run the code to show you how the execution of the program is, and then I will elaborate this particular numerical which I have actually done right over here. Okay, so let me run the program python decision tree.py. As I hit the enter, the program will get executed and it would show certain output. We will come across this entire demonstration as well. So let's see right over here. As I said, that the data set which is provided, that is iris.csv file, is evenly distributed. As you can see over here, the total number of instances in context to the class Setosa is 50, Versicolor is 50 and Virginica is 50. So that means there are three different classes of instances are there in the data set, and they are all evenly distributed. So how did I manage to get these three information? And for that reason, after reading the CSV file, I am giving a call to a wonderful function provided by Panda, and that is called value_count. But before you use this function, let's see which particular feature this particular function will be applicable. I have a feature called target, which is basically my dependent feature. As you can see right over here in the data set, sepal length, sepal width, petal width, these are all independent features. So there are total 4 independent features, but there is one dependent feature which is basically based on that the decision tree is going to implement. So this is my target, this is my dependent feature, and that is what I'm referring right over here. So I'm saying that the data frame, that the instance which I created from after reading the CSV file, inside that instance there is a particular feature called target. That is what I'm actually trying to pinpoint. Using that feature, you give a call to a function called value_count. What this particular function would do is it will count the number of instances in context to the each class that is present in the data set. So as we saw that in the data set there are 3 different classes, so it actually counted how many number of instances are there, and after counting that, it actually stored it inside this particular reference called class count, which I have given a name, and that's what I'm printing right over here, whose output you are seeing. So nicely it has distributed that there in the data set there are 3 different classes. One is Setosa with the 50 record, Versicolor with 50 record, and Virginica with 50 record. Okay, so that's what we found from the value_count function present inside the pandas library. Now what we will do is that, of course, we have to find out the total number of records, so we can simply go for length function, mentioning this particular reference, and it would give me the total number of instance present in the CSV file, and that is called 150, which we can see right over here. 50 plus 50 plus 50 would give us 150. So that's what we saw over here. Now comes to the very important part of the story, and this is where actually this particular video is going to be very helpful. We have to find out something called entropy. That is something we need to find out, and while finding out entropy, we need to make use of probability. So what we are going to do is that we are going to find out the probability of Setosa, probability of Virginica, and probability of Versicolor. we know that there are 50 instances are there. Total number of instances is 150. So 50 divided by 150, we are getting a value of 0.3333. so this is the probability value in context to all these three particular set of data. So that's what I'm doing right over here with the help of this particular statement. So class count actually store all these three informations divided by the total sample. The total sample is the length, that is 150. So in class count, Setosa has got 50, so 50 upon 150 for Setosa. Similarly, versicolor is 50, 50 upon 150 for versicolor, and Virginica is also going to have 50 instance upon 150, and that's what the probability which we will be getting, and that's what I can show you right over here also, which I also did it by myself. I calculated it, and then eventually we got this result, and that's what I'm seeing right over here. So once the calculation has been done, I am printing this value. So by virtue of this line, I repeat, by virtue of this line, you're able to see that the following probability in context to three different classes is presented right over here. Okay, so that's what I have done over here. Okay, why did I need to calculate probability? Because when we're talking about decision tree, we have to deal with entropy, and in order to work on entropy, you need to find the probability of each of the classes that has been used in the classification data set. And as I said, we are working on decision tree, so decision tree is going to work on classification type of supervised learning algorithm. So for that reason, we need to find the probability of each of these three classes, and with the help of this probability, now we will be able to find out the entropy. And here what I have done is that I have really implemented the formula of entropy, which is this particular formula. Let me show you what I did in the numerical. This is what the formula you will be seeing in any of the book or any of the manual, that is minus summation of I represent the number of classes that is there in the data set. So over here we have got three different classes: Setosa, versicolor, and Virginica. So that is what the I represent. The probability of I, the probability of I means probability of Setosa, probability of versicolor, probability of Virginica. So in that context, it is saying the probability of I, and all these is going to be summed up together into log probability of I base 2. This is very important. This is the formula that we will be using to find out entropy. So I repeat, it will be the summation of all the classes that has been there in the data set, whose probability I have to find out, into log of probability of those classes base 2. So now how do I represent this entire thing directly in the code to find out the entropy? So for that reason, NumPy will be used in this context. So let me show you how NumPy is coming in picture. As you can see over here, summation is there with the minus. So minus np.sum. So this sum is going to do the summation of entire thing. So, and this is the portion that is there inside the sum function. So whatever calculation will be done, and on that the summation is going to work. So summation will be done with the help of np.sum, and we have already find out the probability of the respective classes, that is 0.3333 in context to all the three classes. That is what the probability refers over here into. So this into is there, and that into is represented by log of into log 2. So log 2, how do I get to log 2? The log 2 will be, I mean, log base 2. For that reason, we are going to use NumPy. Again, NumPy comes in picture, NumPy dot log 2, and the log 2 will be working on the probability. So again, the probability comes over here. So look at the function very properly, and this is how the formula of entropy has actually been figured out. So let me explain this portion once again. So minus summation of each of the classes of probability. So minus np.sum, and within that, that's an outer function, and then we have got the probability into the log base 2. So we will be using np.log base 2, and the probability is right over here. So if you plant all these values of probability, you are getting it from here if you are using that, and then eventually we'll get to find the entropy, and that entropy I have printed right over here. So let me show you what is the value of entropy over here. We are getting a value of entropy as 1.5849 so on. So how did we get this particular value? And that's what I will be showing right over here. So if you look at this formula now, you have to implement this formula for all of these classes. So it would be somewhat like this: minus probability of Setosa into log probability of Setosa base 2. This is for the Setosa, plus, because summation is there, plus probability of versicolor into log of probability of versicolor base 2. This is for the versicolor, and lastly we have to go for virginica also. So probability of virginica into log of probability of virginica base 2. So this would be, and the outer we have a form minus, and this is the entire representation of the formula for entropy. So now what I did is I calculated one of the class. So let's consider the Setosa. I'm doing it. So we know probability of Setosa is 0.3333 into log of probability of Setosa is again 0.33 log of 0.33 base 2. If we calculate the log of 0.33 base 2 would be minus 1.5846, and that's what I'm multiplying with minus 0.33. I will be getting a value of 0.52832. This is approximately, I have got it, and this is one of the probability. Keep it in mind, we are working on one of the probability. In this way we have got to go with the 3 probabilities. So for that reason what I did, this, since the probability value is same for all of these different classes, so for that reason what I did is I have multiplied that. So 3 into 0.52833. Once I did this multiplication, I am getting a value 1.58496, and that exactly what you are seeing right over here as well, 1.58496, and so on and so forth. So that's what I have calculated by myself using the expansion of this formula, and that what has been done with the help of this particular line which the entropy calculation is doing. Now why entropy is so important? The reason is when you will be going for the decision tree implementation, you have to bring down your entropy to the 0. Unless and until your entropy is not 0, it would consider as impurity. So this entropy is basically going to consider the level of impurity. That means you are unable to distinguish the data. So for that reason you have to minimize it, and that's where the split, that means you are splitting your data into different levels, and as you do that, eventually your entropy would come down, and it would come to the, until it is 0, that the split operation will be going on. So that's the reason entropy calculation is very important. Okay, actually like you will simply call the decision tree classifier and it will do the work, but since this is a particular feature that works behind the scenes, so I have emphasized more on this particular concept to tell you that how exactly the split, that means the decision tree is getting split into multiple levels, which I would be showing in my next video, because this video is going to be a pretty long one. So in my next video you will be seeing that the decision tree has got multiple levels. So how exactly it has been determined that the level will be there, how many level will be there, so that where the entropy actually plays a crucial role to figure out that. Okay, so we saw that this is the value of the entropy that we got. Okay, great. Now we have to go about the machine learning part, and for that reason what we need to do is that we have to split our data set into 2 segments. So, and that brings us the capital letter X. So X would be holding all the features except the dependent feature. So that means it will be holding these 4 features. So for that reason what I have written is that data frame dot drop. So you are going to disregard the field or the feature that is named by target, and you are doing it at the column level. That means you are discarding this particular column, the target column you are discarding it, this column you are discarding it. So for that reason I said that drop, this is the target is the name of the feature, so you are discarding that at the column level. So that means this particular column is not included inside the X. So if you print the value of X, you would be seeing that these 4 features are there, right over there. So that's what I have mentioned over here. So you're dropping a particular feature because you have to split the data into 2 different sets, where there would be independent feature and there would be a data set that would be dependent feature, and that is where Y comes in picture. So Y is the reference that would be holding only the dependent feature. So X, capital letter X, is going to hold all the independent feature together, that is the 4 features, and the Y is going to hold only one of the feature, and that is the dependent feature. So that split has been done over here, and we need to do the split because we have to use the split in context to train underscore test underscore split function, and this function is what present inside this learn.model selection. So from there we are going to use it, and this is a very common function. Definitely you must have seen this function number of time in different supervised algorithm. So over here you are passing, I'm passing 4 different parameters. The first parameter is your independent feature, that is X. Y is your dependent feature, and how much is the portion of data that what you want to supply as a training, I mean the testing data, test size, the test size 0.3 means I want to supply 30% of the data. So 30% of the data, that means 30% is how much? Let's see. 30% is, so total number of data we have got is 150 into 30 divided by 100. So we have got 45 rows to be assigned. Yes, so out of 150 row, 45 rows I'm keeping it for my testing part. So rest 105 I'm going to use it for my training part. Remember, the total number of rows which we have got is 150. Out of 150, 30% I'm using for my testing part. So that means 105 rows I will be using for training, and 45 rows, explicitly 45 rows, I'm keeping it for my testing. So that's what I have done mentioned over here. So this thing will be split into 4 different references. So X train is going to hold the independent features. Similarly, Y test will be holding the independent feature. Remember, X train will be having 105 instance, Y X test is going to have 45 instance. Similarly, Y train is going to be your dependent feature, that is 105, and Y test is going to be another dependent feature which is 45. So X train and Y train together is going to be 105. X test and Y test is going to be 45, as since I have gone for the test size of 30%. Okay, so now we are giving a call to the decision tree classifier that is coming under the sklearn.tree, because decision tree is going to have a tree representation. So from there the tree is coming in picture. Here I have mentioned that how many level of tree you want. You must have seen that this particular constructor may be without parameter also, but in my next video I'll be talking about this particular level, why I have gone for this level. But until now you consider that there would be 4 different levels, although I'm not showing you the level because I'm showing you the heat map over here. So the next video I will be talking about the level part, and there where you will be seeing that there are total 4 levels which would be there, and eventually when it reaches to the very last level your entropy would bring down to 0. So that's how the entropy is going to work. So here is my reference that is called dt underscore model, that is decision tree model. And now we are going to perform the training part, and while we are doing the training we are providing your independent features, and subsequently we are providing the dependent feature as well. Okay, so that's where the training has been done. So once the training is done, now comes the question of prediction, and for that we are going to use a function called predict, and this predict function we will be using the test data set, which is a 45 instance. Remember, while training we have made use 105 and the rest 45 rows, because 30% we took it for the testing part, is used for the prediction. So finally we have got the predicted result right over here. So Y predict is actually holding the data that is been predicted. So now we will be going for a comparison between the actual data that we have got in our Y test. So this Y test is holding the actual data, and Y predict is going to hold our predicted result. So we would do the comparison, and for doing that comparison what we would be doing is we are giving a call to like we are creating this pd.data frame. Here we are passing our Y test. So Y test is actually the data, that is actual data, that is what I'm passing over here, and Y predict is what I'm passing over here. And with that we are creating this particular reference. Well, I can print that record, so it will print you 45 rows. So let me do one thing. Let me stop this application for the time being, and let me clear the screen, and let me rerun the code once again by uncommenting this line. Here we will be seeing the comparison between the actual data and the predicted data. So let's run the code once again, and as I hit the row here it comes, and a big chunk of record is right over here. As you can see, it is from 0 to 44. As I said, 45 rows will be used for the testing part, because 30% we have taken for testing. Now if you look over here, this is the actual data, that is of your y test, and this is your predicted result. So it would be very difficult for you to differentiate between which one is the correct one. If you see subsequently, you will find they are all similar, but what I have seen one portion, that is this particular row, if you take a note, that means the row number 38 is actually 0 to 37, 38. Here the actual data is versicolor, and but the machine has predicted that it will be virginica. So this is where a difference would come in picture, but this is very bad way of figuring out how much is the difference or how many is the actual difference that has taken place. In this way you cannot differentiate, and that brings us to something called the confusion matrix. So confusion matrix will help us to differentiate between the actual data and the predicted data, and that's what we will be seeing over here. We will check the accuracy also, but before that, let's see the confusion matrix. So I have created the confusion matrix with the help of the y test, which is my actual data set, and y predict is the predicted data right over here. So that's where the confusion matrix is coming in picture, and I want to give a graphical representation of that in the form of a heat map so that we can see in a better way. So here, for that reason, we are giving a call to a class called confusion matrix display, where I'm passing this particular reference, which is my confusion object, and I am going for the labeling. So display underscore label. Remember, inside this particular data model, this model which we have trained, here it has able to figure out the different labels, because we have got 3 labels. One is the setosa, versicolor, and virginica. So those 3 levels should also be there in my predicted data set as well. So for that reason, display label, we are actually showing the label that is there in the prediction as well as in the actual data set, and that's what you can see right over here. So this is the row that has been shown, and this is the column that has been shown over here. So for that reason, we have to print the display underscore label and the exact labeling that has been done in the data set, that what I want to display. And here I have gone for the color blue to show me these different colors. Let me show you something which is very interesting over here. Remember, we have got total 45 instances. What it is saying is that setosa, it is saying there are 16 instances are there in setosa, and it has actually correctly figured out those 16 instances. So the actual label is 16, and the prediction is also 16. That means it has been able to identify 16 setosa correctly, and there is no wrong instances are there. That's the reason it is 0 and 0. Whereas in case of versicolor, as we can see right over here, the total number of instances for versicolor is 17 plus 1 is 18. So there are total 18 versicolor instances are there, out of which correctly it has predicted 17, but there is one instance is there where it has wrongly predicted, and that is it has predicted as virginica. So the correct prediction is prediction of versicolor is 17. It has correctly predicted. So this particular cell is saying that the correct prediction has been 17, but one data or one instance is there where it has wrongly predicted. It should have been versicolor, but it has been printed at virginica, and that is what line number 37, which you can see right over here. The actual data is versicolor, but it has wrongly printed as virginica. So that's what it's been showing. So total number of versicolor is actually 17 plus 1, 18. Similarly, virginica, the total number of record is 11, and it has actually correctly pointed out that all those 11 record. So that means 16 plus 18 plus 11 is equals to 45. So there are total 45 instances are there. So with the help of confusion matrix, you can rightly compare how many are the correct result, how many are the incorrect result. So that's what we are seeing right over here. Again, I'm saying there are total 45 instances are there, out of which setosa correctly pointed out 16. There is no incorrect result. Where in the case of versicolor, there is 17 corrected result are there, and there is one incorrect result is there, which total 18 is there. And virginica, in context to virginica, there are total 11 record are there, and they are all correctly pointed out. And that's what we are being shown right over here with the help of matplotlib PLD, and eventually we are getting this result. So that means since there is only one incorrect result, so let's check the accuracy. the accuracy is 0.97. that means 97% accuracy, which is almost close to 98% accuracy is there. Now how did we get this 98 accuracy? And that is where a small formula is there, that also I'm showing you. This formula is like this: when you calculate the accuracy score, what it does is it will find out how many are the correct result. The number of correct instances is 44. There was one incorrect instance, right? So the number of correct result was 44 divided by total number of predicted results. The predicted result is 45, so 44 divided by 45 would be 0.9777, something like this. So that is what your accuracy level is. So that's how you calculate the accuracy level. Okay, so with the help of confusion matrix, we saw how many are the correct result, how many are the total result, and how many even are the incorrect result, and based on that we are finally finding our accuracy level as well. The video has been pretty lengthy. I am again saying there is one more part that is left, where I will be showing the entire decision tree leveling, that I will be showing it. But overall, in this particular video, if you go through this code, I believe you will understand how exactly the concept of a decision tree working is taking place, and entropy as well as the probability part and the confusion matrix. These things would be crystal clear, right? So just wait for my next video, where I'll be showing the leftover part. Until then, have a nice time. Bye bye.